my name is Nathaniel Cook. So before I even get started into my talk, I just wanted to, who was at the talk earlier this afternoon in McKinley on forecasting automation robustly? Okay, so some of you guys gave the talk, thank you. Okay, because it turns out my talk's actually highly related to their talk, so I'll probably be referencing their talk a few times today on the fly here, so we'll see how that goes. But yeah, totally unplanned, but it was exciting. I enjoyed their talk. Okay, so today I'll be talking about forecasting time series data, specifically with the tick stack. I'll explain what that is, and at scale, and I'll explain what I mean by at scale. So, like I said, I'm Nathaniel Cook. I work for a company called InfluxDB, and we build a set of open source products that we call the tick stack, and they're a time series data processing platform. So hence time series forecasting, time series products. This is great. So with that, we'll just jump right in. So why am I here? A couple months ago, Facebook released their profit algorithm that these guys talked a little bit about previously. And I read up and I was like, oh, that's interesting. That's kind of fun. So I tried it out and had a good experience. So I'm here to share that with you and to see how it works out. So an overview of what we'll be talking about today. First, let's give a quick review of what I mean when I say time series data forecasting. Really simple. And then we'll talk about the challenges of scale and what I mean by when I say scale. And then we'll introduce in a little bit of depth the Facebook profit algorithm and that procedure and how that works. And then the majority of the talk will be focused on an example walkthrough, an experiment I did using their algorithm and their procedure, and how that turned out for me on some example data. And then we'll present some learnings and then wrap up. Great. So what is time series forecasting? Well, assuming that the past has any relation on the future, we can predict future values based off past values. And so the idea there is you develop a model, doesn't matter what the model is, but you develop a model that says, based on these past values, what should my future values be? And so that's what we mean when we say time series data forecasting. Then you need to compute the accuracy. And the earlier talk gave us a nice huge list of a dozen different metrics that you can use to compute the accuracy of your time series metric. Today we'll just focus on one, the MAPE, mean absolute percentage error. But you could switch it out for any of the others that they talked about today. And then finally, another method is to use baseline models and to compare your predicted model against other models that are more simple to make sure that your baseline model hasn't just gone totally crazy and done something weird. Okay, so here we go, simple hand drawing, time series data on the left. You've got the red line, which is your raw data, and then you predict, it's going to do something like the blue line, right? And then the black tick represents the current time. And then later, real time passes, and then you actually get the raw data for the data that you predicted, and they overlap because they were for the same period of time. And then you compare them and you say, well, how good were they? Right? And this is where there's multiple different metrics. So that the MAPE metric is basically you take the percentage error between those and you take the mean across that entire interval and you get a number between 0 and 1. And 0 means you predicted it perfectly because you had 0 error. And 1 means that the relative values was 100% off. And it can even go above 1 actually if you have really, really bad error. We'll actually see an example of that today. Okay. So what are the challenges of forecasting at scale? It's actually very simple. It takes a lot of time to get a model to work. Right? So most of the time when you put a model in production, it's the model that's doing something awesome. And you can spend a lot of time tuning it and optimizing it and making that model work for you. In this case, we have lots and lots of models. And so we can't spend time with each of the models. We have to make sure that on a big scale that all the models individually are working well, but we don't have time to sit there and babysit each one. So we need to design a workflow and a system where we can minimize or in fact eliminate the time we spend on any of the models. Great. So this is where Facebook's profit procedure comes in. And they talk about so today's talk isn't just about the technology. It's also about the people involved, where the people and the teams and the interactions and how communication happens, and a workflow so that the communication is effective and efficient. So the Facebook paper called Profit didn't just introduce a model or an algorithm, it also introduced this workflow or this procedure to go with it. So we'll talk about that here. So first, what was the algorithm? It's actually really simple, and it was intentionally very simple. It was a general additive model, they call it. Basically, your predicted value is y, there on the left of this graph here, of this equation. And then you had 3 terms, and you just add them together, and those terms equal your predicted value. Okay, so what are those 3 terms? The first term is a growth term, and it just kind of predicts the overall trend up or down of whatever series you're forecasting. The second term was a seasonality term. So the domain in which this algorithm tends to work well are business metrics. So for example, things that have daily cycles or weekly cycles or monthly or yearly cycles. These kinds of seasonal cycles in them. And so the seasonality term would learn about those things. And then lastly, you could add in a holiday term, which would say, hey, July 1st, everybody, or July 4th, wow, July 1st. July 4th, everybody's shooting off fireworks and nobody's doing any work. And so we could expect something different on that day. And so you can account for those kinds of things. Okay. So that was the model, the algorithm. So what's the workflow? And so Facebook labeled it analyst in the loop. Or basically, put the analyst in there, who's someone who understands basic statistics but isn't necessarily a statistician, and who isn't necessarily a DevOps guy either, who's running around and setting up servers and coding. It's just someone that understands the domain of the data and wants to make sure that the models are working well. So this 4-step cycle or workflow is first you create a model. And so in this case, creating a profit model, right? Model based off the profit algorithm. And then second, you evaluate that model based on some metric. Like I've repeated, we're going to use the MAP, MAPE metric today. Then at the bottom, you surface all of the forecasts that have problems. So we'll define what they have problems means in a minute. But you surface them and you bring them forward so that you know that those are the ones you need to spend time on, as opposed to all of them. And then you visually inspect the model. And you look at it and go, oh, this is what's wrong with it. And then you fix it, and then you get back to the top. So the analyst need only participate in these purple steps. These green steps are fully automated. And they can happen in the background. You don't have to touch them, you don't have to think about them. They just run. And so the analyst just simply sits there and spends their time working through the problematic models, fixing them and tuning them, and basically gets this nice workflow where the problems surface on their own, and they can spend time just whacking a mole. And that sounds boring, but it's a lot better than not knowing where the mole is to whack. Right. Horrible analogy, shouldn't have made that up. Okay. Great. So now we're going to jump right into the example. Work through the data. Before I do that, are there any questions? Starting off, right now, I kind of like this a little bit more interactive, so if you've got questions. Okay, wait, yes, go ahead. Say what?
Canadian.
Am I Canadian? No. Sorry. Is it the mean? Huh? Okay. I am not Canadian. Nope.
No, that was July the 1st thing.
Oh, okay.
July 1st is Canada Day.
Oh, July 1st. Nope, that was just, I have no idea what that was. Yeah. Great. So, for this example, I went and got a data set that I thought would be fun to look at. So, I went to GitHub, and I found an awesome Python list. You guys seen these awesome lists on GitHub where people compile these lists of awesome things. And so, there's an awesome Python list out there. It's got about 400 Python projects listed in there under different categories for different things. And I went and I grabbed their GitHub stars. And so we can use GitHub as a relative proxy for popularity of the project, and it's a nice time series data, so we're going to play with it. So, the cool thing about grabbing an awesome list, as opposed to just grabbing the top 100 or 400 repos, was it wasn't the top, right? So in this list, it's a very, very heterogeneous list of projects that do very different things. And that's going to be important in a minute. So some of these projects are really small. There's a dozen of these projects that only have 30 stars. But they're on this awesome list because they're awesome somehow, but only 30 people agree. And then there's some really large projects on this list as well. Some projects that have 30,000 plus stars, and they're very large. And then these projects range from very different use cases. Some of them are really simple, like CLI tools that have nothing to do with data science, and they're just happen to be written in Python. And then some of them are like SciPy and these other important NumPy and important Python projects. important to us. And so they're very, very diverse. So my point in pointing out the diversity of these projects is that you can expect different growth patterns on these projects, right? The time series growth on each of these projects is not going to be the same. They're going to have different characteristics, they're going to be unique in their own way, and so we're going to learn about them. And then likely, in a similar way, we have new and old projects. We have some projects that were there on like day one of GitHub, and so they have dates all the way back to 2008. Some of them are started earlier this year, and so only have a few months of data. So we've got this very heterogeneous set of projects, but then the data is all the same in that it's just a simple growing curve of stars over time. Okay, so what's our goals with the example? Well, we want to forecast the future stars of these projects for all 400 of these repositories on GitHub. And we want to be able to fix any forecasts that we set up initially that are broken or just really bad. And we want to do it in a repeatable manner such that this costs very little overhead, very little time and resources on an analyst or developer so that you can do this at scale, right? And 400 is pretty small, right? But the idea here is, these could be different communities, right? So the example that Facebook uses is they have lots of communities. Think of Facebook like different groups and things like this that they have. Each one of those has its own growth and things like that. And so they're managing many, many, many of these. So that's a little insight into how this could be used on a bigger scale. Okay, so to do this in a scalable manner, we need a nice platform. Or it'd be nice to have a nice platform. So this is where the tick stack comes in. Okay, so let's take a minute here and learn about tick stack. So first, TIC is an acronym for TSEK and for the 4 products that make up the stack. So Telegraph is this first piece. And it's over here. And Telegraph the Tiger, it's pretty awesome. And Telegraph is a collection agent. So the idea here is it's the thing that goes and gets your data. We're not using it in this example per se, just because I already collect the data just by scraping the GitHub APIs. But in a more real-time environment, you need a way to kind of ingest your data in a real-time way, and that's what Telegraph can do for you. Okay, so then the next piece in the stack is InfluxDB, and that's the database that stores the time series data. It's optimized for storing time series data, and it has a SQL-like query interface so that you can start your data in, query it back out, do kinds of operations that you would typically do on time, aggregations, selections, et cetera, et cetera. Okay, so then the next piece is Chronograph, which is up here. Chronograph Giraffe. We're in the Chronograph Giraffe today. He's pretty awesome. This is the visualization engine to this stack. So it allows you to visualize, graph your data, build basically the GUI for the rest of the stack. And so that's what Chronograph does. And then last is Kapacitor. I'm actually the developer of Kapacitor, and it's the real-time processing engine on the data. So the database allows you to write the data in and query it back out with some basic aggregations. But when you want to start running machine learning models or other complex things on your data, that's when you bring in Kapacitor to be able to do all of this processing. So an analogy, and this is very rough, but it's probably better than the whack-a-mole one. But Kapacitor is kind of like Spark. Apache Spark in this sense. Specifically built obviously for the time series use case and for this stack. Okay, so that's the tick stack. I'm going to use it today to model all these 400 GitHub repos and forecast their stars. Okay, so how are we going to do that? First, we just need to store the data in InfluxDB. That was relatively straightforward. Downloaded it, well, relatively meaning all of the data cleaning takes a little while. But download all the data from GitHub API, rejigger it, store it in InfluxDB as the database. So now in the database, we have a set of timestamps for when a user starred the repo, and then GitHub terminal, or in InfluxDB terminology, we've tagged that data with which repository that star was for. And tag just means an index column on your data. So then we use Kapacitor. Kapacitor runs tasks. It's like a job scheduler. It runs tasks and does work on your data. So we're going to use Kapacitor tasks to do all of the automation steps of this workflow, the 4 steps there. The second and third steps are the ones that are automated. We're going to use Kapacitor to run those tasks for us and evaluate and surface problems with our models. And then third, we can use Chronograph to inspect the models. Just visually, just look at them, that third step there in the step. And yeah, okay, so here's a graph. Hopefully it looks horrible to you, because it is horrible. This is a graph of all 400 repos and their stars. Very useful. I have great insights from this data. I mean, you can pick out a few things, right? Like you can see that there are like 3 projects that are way high above everyone else. You can see that some exhibit these really sharp like growth periods that are like basically vertical, and then kind of just have like linear exponential growth after that. But for the most part, yeah, you're not going to glean a whole lot from that. And you could go look at them one by one, but that'd take all day. So not very helpful of a graph. But there it is. Okay. So step 1, we need to create some tasks in Kapacitor to do our evaluation step. So our plan here is to create 3 tasks that model and forecast the data. 2 of them we're going to label as like baseline models that are really, really simple forecasting models. And by simple, I mean the mean one literally takes the mean of the data and says, that's what the future value is going to be, is the current mean. So very, very simple model. But it actually turns out to be quite useful later for just sanity checking our models. And then the other one is an exponential smoothing, or also known as like Holt Winters. It's a recursive algorithm where you take the past history state and you build up on it, and you can predict out the future one. It's pretty straightforward, not very complex, not nearly as complex, for example, as the profit model. And that allows us another baseline, just hey, make sure that things are within tolerance. Okay, so then we have our profit model. So Kapacitor is a system, and I'll talk a little bit about how it works in a second, but the profit model is written in Python and R. Kapacitor is not written in Python. It's written in Go, if you care. And so how do we talk to it? Well, Kapacitor has a plugin system, UDFs, user-defined functions, and so we can just call out to the Python code and run the profit model from there. And it's efficient, uses protocol buffers for the data transfer, et cetera, et cetera. And okay, so we have these 3 tasks, and these are actually task templates, meaning that we set up a template for the mean task, the Holt Winters task, and the profit task, and then we instantiate one of those tasks for each of the GitHub repos that we have. So we have roughly 1,200 tasks. And the reason why we're doing all of these different tasks, because that sounds like, wow, 1,200 tasks, why am I managing so many when I only had 400 to start with? Why are we blowing up? The reason is it gives us the ability to set different parameters per task per repo. And it doesn't end up being a difficult thing to manage, because you don't touch into the tasks unless they have issues, and then you just can tweak them. So again, the task just allows you to have custom parameters per model, which we'll see in a second is useful. Okay, so that's step 1. I just used GNU parallel, a little CLI command there, and just said, boom, define all these tasks, done. And then the way Kapacitor does the template system is any updates to the template update the rest of the tasks. So you don't end up ever really interacting with the tasks after you've defined them. Okay, so bam, here's some code. Probably looks really unfamiliar to you because it's definitely not Python. And yeah, let me tell you what this is. So who here was at the Dask tutorial yesterday? Okay, so a smaller percentage. Okay, so the way Dask does their computation model is they model the data as a DAG, a directed acyclic graph. Kapacitor does the same thing. They take the data that, the pipeline, like first you're going to sum the data, then you're going to take the mean, then you're going to do whatever. And they build this DAG, which is the pipeline or the data flow of your data. Kapacitor does the same thing, and it executes this DAG based on the time series data that's flowing through it. The way you describe your DAG is through a DSL inside of Kapacitor called tick script. Really simple, and this is what you're looking at right here. So the idea here is that each of these pipe characters and the at character, the at just means it's a UDF. Basically think of it as a pipe character. Each of these pipe characters represent an edge in that graph where data is transferred from node to node, and then the node itself is like, what are we going to do at that step in the graph? Okay, so here we're querying the data out of the database. So we're going to select the value. We're getting a little bit of weird formatting on that. There's supposed to be a space between from and source there, and between where and project, but you get the idea. It's SQL-like. This is pseudocode anyway, so don't expect this to just actually run. There's a little bit of boilerplate above and below that I just omitted for brevity. And the basic idea is we select our data, we grab it over a certain historical amount of time, and then we do it every so often. So these tasks run continuously. They're always scheduled, and they just run continuously, so that this is just a process that's just online and running. Then we group by the set of group by dimensions. In this case, it's the project. So we're going to select all the data, we're going to group it by our list of projects, and then we're going to shove it into the profit algorithm, which this basically, like I said, calls out to the UDF and runs the code. So the profit algorithm has a couple of properties that you can pass in that I've abstracted here through the UDF. You tell it, you give it a bunch of historical data, and then you say, well, how far in the future should I predict values? And so that's what this little bit here is we say, you know, how far, we've got a parameter to this entire script that's how far we should forecast, and then we've got an interval per data point, so we divide them. That's a count of how many periods into the future we should forecast. Then the change point prior scale, the talk earlier today talked about using Bayesian inference to detect change points. The profit algorithm uses a similar method to find change points in these data, inflection points in growth. And so you can give it just kind of this value from 0 to 1 that says how aggressively should you look for change points. And so you can pass that in. And then the profit algorithm also returns a confidence interval width. And so you can tell it, you know, again, a value between 0 and 1, typically like 80 or 90% confidence interval, and you can say how big you want those confidence intervals to be. Okay, so there's our template. We can instantiate that 400 times and give it different values. But by default, we'll just give all 400 the same default values. And hopefully it works out for most of them. Okay, so step 2, we need to evaluate these models. And we need to do so in we need to do it for all of the historical data that we have and for each of the different models. Right, so we've got the different projects and the different models, the mean, the hold, and the profit models. And so this is just a simple single task in Kapacitor where we group the data both by the project dimension and the model dimension. And then we compare that data so obviously we'll hold out some of the data, right? So we pass it in the first year of data, we have it predict out a little bit of time, and then we go look at that little bit of time and we see how well it did, right? We compute the error metric. And again, here we are, we're talking about the mean absolute percentage error. We're grabbing that, the map metric. Okay, so here's the task that computes that one. So it's really simple. We've got our source data and our forecasted data. We join them together. They're already grouped by project and model, so we join them on the model or on the project dimension. Then we compute the difference and then divide by the current value. And in this case, we don't have problems when any of the values are 0 because there's always at least 1 star or the data doesn't exist. And so we never have a divide by 0 issue, and we get a percentage error there. But then we want the mean percentage error, so then we just sum up and count all of the different errors in that window of time that we were given, and we bring those back together and compute the mean. And then, bam, we've got our MAPE value, and we write that back to the database. So now we have a database that has the source data, a database that has the forecasted data, and then a database that has the errors. And all of those are over time and as a dimension. So we can track those over time. Okay, so step 3 is we need to surface the problematic models. This is really easy. We now have the data sitting in a database. It's just a simple select query. Just go get me, so we're talking about error, so go get me the top 10 projects that have really high error. Done. And then we just say, over the recent data where the model is profit, bam, there's our worst performers. If you want, you can do the inverse, and you can get your best performing models. And there you go, really simple. You've got a set of all your models and their errors over time in the database. You can just query them back out. So you could even go a step further than just querying them and putting in a table. You can plot a distribution of these. So with the distribution, what I'm plotting here is the accuracy. So the x-axis here is the percentage error as a log. And then the y-axis is just the normalized histogram distribution. So you can see that the mean model here in red, it has like a point that didn't do so great, but overall the error is like, somewhere between 0.01 and 0.1. So, 1% and 10%. So that's not great, but it gives you a good baseline, right? So then the Holt-Winters model actually has this nice slope over here where it gets some that are a lot better than the mean model, but overall still not that much better than the mean model. In fact, in some cases it's quite a bit worse. but still somewhere between 1% and 10% error on the Holt Winters model. So then we have the profit model, which on the whole actually gets a lot more of its distributions down there towards the smaller errors, but it's got some that are really bad. Like this guy's got 250% error. Like he just totally blew it out. The model default values were just horrible and didn't work very well. So hey, that's our problem guy. He's going to be the first one that comes back on that select statement, and we're going to go fix him. Okay? So here's a graph of how you would fix that model. It's a little dark, but we can make it work. Okay? So the top data is both the raw data plotted with the predicted values for all three models. And then this graph is the error being plotted. And you can see over there, the scale is like hundreds of % of error. And this blue line is the profit model saying, I just blew out, I got a ton of error. And it predicts so drastically that the growth curve of this entire project just looks flat in comparison. So this model just horribly predicted the data. And then I just kind of showed it down here. This is for an LP trace, which is like a S trace for Python type thing. And so we've got this table here. I only showed the first entry, but you've got a table here of all 10 entries that are the worst performers. And this is the guy that's on the top. And we've selected him and reviewing that project's data. So we've got a problem. We've visually inspected the data. We understand how it's broken. So how do we fix it? Okay, so the Facebook Prophet gives these simple guidelines, and the whole point of all of this setup and putting this all together is so that you have a very simple checklist of three questions you can ask yourself, and then proposed solutions, so that the process here is really quick and simple. So, first question, does the model have large errors compared to the baseline models? And that one, it was like, yeah, definitely. That was the issue. We'll go look back at it in a second. And so maybe the profit model is misconfigured. Update the model. So then we just know that, hey, the profit model has bad parameters. Let's fix it. Another possibility was that all the models went bad. So even the simple Holt Winters and the simple mean model went bad. Well, in that case, it's likely that there's some outlier in the data just throwing all the models off. Go find it, remove it. Right? That's something that's really simple to do. Right? Third case, the errors were historically good, like they were historically very low, but they just recently spiked. Okay, well, maybe that just means that we had a change in the underlying process of this data, and we just need to go set that as a change point. The profit algorithm will auto-detect those change points, but you can also manually specify them. So you can say, hey, something happened in the data that's different now. Think of it differently, manually, here's the time it changed. And so you kind of get these three, and there may be other edge cases, right? But this is going to cover a very wide breadth of the different ways that your forecasting can fail, and then you can update it, right? So if we look back real quick, the mean and Holt Winters models have very small errors, and they basically follow the raw data, which is in red. So the profit model is the only one having the issue, so that means we're definitely here in case one, where the profit model is the one that's misconfigured, and we need to update it. So I went in, I looked at this one. It also has a very small amount of data. This project started October of last year, so it doesn't have a long history to predict it. And so that was my hypothesis for why it was getting messed up. And you can clearly see that it is thinking there's really drastic change points and really over predicting here. So that initial parameter called the change point prior scale, I just pulled that down. I said, nope, you are not allowed to be as flexible in deciding where the change points are. Let's just pull that down. Okay, so I pulled it down. Here's the updated model. Bam. Profit model still isn't great, but at least it's not 250% error, right? Now we're down to like 5% error. And that was a 10-second change, and then I just kicked off the task to rerun the model, and that took another 30 seconds, and then bam, we fixed this one. Our list of worst performers now has a new guy who's sitting at 7% error. So now we know that our max worst performers at 7% error, still not great, but it's not 250%, and we can now go tackle that one. And that, I don't think it's going to take another minute or two, hopefully, right? So that's kind of the general idea, is to, like I said, and coming back to step one here, is to start with a bunch of data, model it all, compare it to baselines, compare it to whatever metric you want, the mean absolute percentage error, enter the NRSME values, any of those dozens of values. Find the ones, or you could even do multiple if you wanted. You could have multiple graphs down here that's not just the MAPE value, but you could do multiple of them. And then you just get this simple workflow where you've got a table of really bad performing models, you iterate on them and you fix them, and then you can keep your upper bound on your worst performers low. You can keep it down. And then you don't end up spending a ton of time managing these, and then you can trust that the rest of your models are doing really well. So here's the final distribution now of the profit model. The Holt Winters ones and mean ones stayed the same, so I didn't regraph them because I didn't change those. And that point that was way out here at 250%, he's gone. He's back down in the middle somewhere. And so it'd be nice to take off anybody above 10% error, right? Or anywhere near close to that and just shove them back down. But I didn't spend the time to actually do that. But you can now start pushing your distribution down. Okay, so learnings and where we're at here. So we have used the tick stack, the database, the capacitor engine, and the visualization engine. Part of my screenshots were actually from something from Grafana, just because I was messing with stuff there. So if you're familiar with Grafana or Chronograph, they're very similar, and some of my screenshots you probably won't recognize from Grafana. But anyways, that doesn't matter. Use the visualization engine and was able to go there. So forecasting at scale is about reducing the cost per forecast, making that overhead just go way down so you don't have to worry about it. And then you can do that by creating a simple workflow with good tooling that enables the analyst to not have to worry about the complexities of deploying or running the model or anything like that. And so that's what the tick stack provides, is it's this platform on which you can run many, many models, and you can track and rate those models over time, watch how they're performing, and then surface those problems. So there's also a couple of really cool extensions here. Kapacitor actually has its origins in DevOps, meaning that it was first built as an alerting platform. So like if you're running a bunch of servers, the CPU spikes, alert me that the CPU spiked. Which means that Kapacitor has built into it all of these systems and tools to be able to alert you proactively about issues, right? So what that means now is you don't have to actually even go to a Grafana or Chronograph dashboard to look at them. If one of your models starts to go haywire, you just get a page on your phone, and then you go look at it. And then you don't spend your day worrying about this thing. If you're getting silence, things are good. If you hear something, you go look at it. And then it can also integrate into the other side of things where it can, for example, we had a talk just in this room before about using Kubernetes to scale out a large system. Kapacitor can talk to Kubernetes, and it can scale out your pods, et cetera, and it auto-scaling based on these metrics. So if you've noticed, if you're forecasting your data, you could forecast your utilization on your system and auto-scale ahead of demand instead of reactive demand. You could proactively auto-scale. And that's where the power of the tick stack really comes in, is it's got these composable bits where it's got nice decomposed products, the 4 different products that interact together to collect, store, visualize, and process your data. And then they integrated with so many different systems that you can put in this big picture solution. And on one hand, you can use it to analyze and ensure that your models are staying active and staying accurate. And then you can, in the same system, then go take proactive action on those models. And so here's some resources from the talk today, the link to the awesome list, the link to the GitHub Profit paper, and influxdata.com, just to see more about the tick stack and learn about it. And that's what I have for you today. Thank you. Questions? Yes?
So you have the profit equation for growth, seasonality, holidays.
Mm-hmm.
And then you talked about the change points that I'll repeat the first part. So you had the equation for the growth, seasonality, and holidays. And then you talked about the change points that it detected and it got off by 250%. How does it actually predict the graph? And then secondly, how much data do you need to start using something like this?
Yeah, so I kind of skipped that part. So profit has that simple general additive term, like the growth term, the seasonal term, and the holiday term, and adds them together. And it just does an optimization. I think LGBFS is the acronym. I don't remember off the top of my head what that stands for. But it takes the data and it fits using that optimization that can handle constraints and things. And it just fits the data to those parameters. So look at the Facebook profit paper. There's a ton of math behind it. Kind of skipped over that. The important part isn't the algorithm. But I found that it's pretty quick. Doesn't need a ton of data. So I only have a data point per day for the stars data. And that one that was short, so it's like 4 months. So, a couple hundred points, not too many. And it can even predict less if you're trying to predict out less time into the future, right? Thank you. Other questions? Yes.
So does the profit model actually go across the different trend lines? Thank you.
Yes.
My question was that does the profit model learn across the trend lines of time series data, is like trying to learn if one awesome project was similar to another and predict the time series according to that, or is it just for
It's
one?
just per single series.
So that
there's
would be
no
just
like cross
one-
correlations or anything.
Okay.
Yep. I mean, you can do that in something like the tick stack. It can start doing those correlations for you, but the profit algorithm itself is simply about time series forecasting for a single series.
Okay.
But it's fast, so you can run lots through it.
Just a question on Kapacitor. Is it like tightly integrated into InfluxDB, or is it like a separate processing framework?
Yeah, so Kapacitor is a separate process, and it's tightly integrated with InfluxDB in that it can consume InfluxDB, but it can also consume data from other sources as well. And so it just has an API where you write data to it because it's stream processing, or it can go query the data. And so either way you want to do it, it can stream the data live to it, or you can just have it query back out of InfluxDB. But it can run independent of InfluxDB if you want it to, that kind of thing.
Can you do aggregations as well?
So the question was, can it do aggregations as well? Absolutely, yeah. So I showed you some of the more complex features of Kapacitor where it can actually call out to a Python model for the profit algorithm. But it can do a lot of basic things too, just like simple aggregations by dimension and time and these kinds of things. Well, thank you very much.